Welcome to The Explainer. Today, we are pulling back the curtain on two of the most fundamental machines that, and this is no exaggeration, literally build our modern world: the drill and the lathe.
I mean, really think about it. How does that happen? It might seem like some kind of magic, but it's not. The answer is actually in a powerful and incredibly precise process of subtraction, just a careful, controlled removal of material to reveal the shape that was hidden inside all along.
And that, right there, is the core idea we're digging into today. It's called machining. And whether you're talking about the engine block in a car or a tiny little screw in your glasses, pretty much every metal component you can think of owes its existence to this process. I love this quote from our source material because it just perfectly captures the lathe's importance. It isn't just another tool you see. Its history and its incredible versatility make it a true cornerstone of manufacturing, kind of like the ancestor to all the modern machinery we have today. Okay, so here's our game plan. We'll kick things off with the art of shaping metal itself. Then we'll zoom in on the drill for making holes and the lathe for shaping cylinders. We'll even get into how you hold the workpiece, the amazing cuts you can make, and we'll wrap it all up by showing you why this is the true foundation of all manufacturing. So, at the very heart of all this machining stuff, there are two really distinct approaches. And you know what? They're surprisingly simple to tell apart. It all boils down to answering one single question: what is spinning? And this chart lays it all out. It's this beautiful, fundamental difference. With a drilling machine, the tool, the drill bit, is what spins to cut a hole in a part that's held perfectly still. But with a lathe, it's the complete opposite. The part itself spins, while a stationary cutting tool is fed in to shape it from the outside. It's a simple, elegant opposition. So the big takeaway here is that a drill's main job, its whole reason for being, is to create internal cylindrical shapes. Plain and simple. It's all about making holes. All right, let's dive into our first machine. We're going to focus on one of the most common types you'd find in just about any workshop: the sensitive drilling machine, which you probably know better as a drill press. You know, these parts all work together as a single system. You've got the heavy base for stability, the column acting as a backbone, and the table to hold the workpiece. Up top, the drill head has the motor and the spinning part, the spindle. Now, here's the cool part. It's fed into the material by hand. That's why it's called sensitive. The operator can literally feel the tool cutting into the metal. Okay, so we've made a hole. Now, let's pivot to the machine that shapes the outside of a workpiece, the classic engine lathe. If the drill makes the hole, well, the lathe makes the shaft that's going to fit right inside it. And just like the drill, it all starts with a rock-solid foundation. The bed is the backbone of the lathe. And on top of it are these incredibly precise tracks called ways. Any little inaccuracy in these ways will mess up the accuracy of the entire machine, so their quality is absolutely critical. Now, think of the headstock as the engine room of the lathe. This is where the motor lives, along with all the gears for changing speed, and the spindle, that's the rotating shaft that actually holds and turns the workpiece. All the power and precision of the lathe, it starts right here. So what happens if you're working on a long, kind of thin piece of metal? As it spins, the force from the cutting tool could make it bend or wobble, right? Well, that's where the tailstock comes in. It just slides along the bed to support the far end of the workpiece, making sure everything stays stable and accurate, even over really long distances. And this is where all the action happens. The carriage assembly is the control center. It holds the cutting tool and moves it with incredible precision, either parallel to the workpiece to change its diameter or perpendicular to it to create flat faces and grooves. Look, you can have the most precise machine on the planet, but a perfect cut is absolutely impossible if the workpiece isn't held securely. This is where specialized work-holding devices come in, and trust me, they are an art form all on their own. The most common way to hold work is with a chuck. And right away, there's this classic trade-off. On one hand, you've got the three-jaw chuck. It's fast, it's convenient, the jaws all move together to automatically center round parts. But on the other hand, the four-jaw chuck gives you so much more versatility and a stronger grip, because each jaw moves on its own, letting you hold all sorts of irregular shapes.
And it doesn't just stop with chucks. Oh no, there's a whole world of specialized tools. You've got centers to support long shafts for maximum precision. A faceplate can hold massive or just plain weirdly shaped parts. And you can even use special rests in the middle of a long part to keep it from bending while you're cutting. So, once the workpiece is held firmly in place, the lathe's true genius is revealed. By just controlling the movement of a simple cutting tool, an operator can perform a massive, almost endless range of operations.
You know, the most basic operation is often the very first one you do. It's called facing. The tool moves from the center of the part outward or the other way around to create a perfectly flat end. This gives you a clean, true surface that all your other measurements can be based on. And this list, believe me, we are just scratching the surface of what's possible. You can create simple cylinders, stepped shafts, cut grooves, even produce the threads on a screw. The lathe can even create that grippy, diamond-shaped pattern you see on tool handles. That's called knurling. It's one machine with endless geometric possibilities. Now, this isn't just about brute force. It's applied mathematics. To create a perfect cone, or a taper, the operator uses this simple little trigonometry formula to calculate the exact angle to set their machine. It is the perfect blend of hands-on skill and fundamental geometry.
So why does any of this matter? Because these operations that seem pretty simple, drilling a hole, turning a diameter, cutting a thread, they are the absolute building blocks of nearly all modern technology.
Check out this number. It comes right from a problem in one of our sources. 3.78 minutes. That's the calculated time it takes to grab a raw 80mm steel bar and transform it into a complex, two-step shaft using a lathe. In less than 4 minutes, a basic machine turns a simple rod into a precise, functional component. That is the power of machining. So next time you're out and about, just take a look around. From the engine in your car to the pen on your desk, every single cylindrical part, every screw, every shaft, it all started as a simple piece of raw material. The legacy of the drill and the lathe is quite literally all around you, hiding in plain sight.